Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
So previously we were discussing about the dining philosopher problem. Just introduce that, right? So where we know that there are five different philosophers. Uh, Philosophers are commonly doing the two jobs. First one is to think, and when they think, they don't do any other job. And second thing is that after thinking for a lot of time, they may get hungry, right? So what they do, they take up the two chopsticks present adjacent to them, right, and they will start eating rice. Okay, now, right, a person needs two chopsticks in order to eat rice. So every person, every philosopher is going to think for a random amount of time, and they're going to eat for another random amount of time. So the availability of chopsticks is a bigger problem, correct? So we know that this is the issue, right? How to deal with this dining philosopher problem, right? So the simplest solution over here is, let's directly go to, we can explain this in our own words, right? So we'll skip writing up of that part and we'll directly move on to the part which gives the solution of this. Okay, so the solution of this problem is like this, right? Okay, the simple solution to dining philosopher's problem is we try to represent each chopstick. Okay, try to represent each chopstick with a semaphore, right? In the sense, a philosopher tries to grab a chopstick by executing the weight function, weight operation. We know that semaphores are are going to hold the integer values, and with respect to each of the semaphores we have two functions. One is weight and one more is to the signal operation. So the meaning is, when we say that okay, use a semaphore to represent the chopstick, means, right, uh, a philosopher when we try to represent that, uh, we have a philosopher who is going to grab a chopstick, a philosopher who wants to grab the chopstick, uh, executes which function? It's a wait function. It's a wait function, right? On that particular semaphore function, on that semaphore, because every semaphore is associated with a chopstick. So whichever chopstick you want to pick up, you have to execute weight operation, because whenever it is weight, others cannot uh, deal with the same chopstick, correct? And the philosopher say releases the chopstick, whichever chopstick a philosopher wants to release. Okay, what has to be done now? You have to execute. So by executing the other function, which is the signal. Okay, operation on the semaphore, in the sense the semaphore which is associated with the chopsticks that the philosopher wants to release. Alright, now let us have a common data shared, right? Is nothing but the semaphore itself. The semaphore is shared between uh, all the processes which using which we try to model the philosophers picking up or releasing the chopstick. Okay, so let's try to define the shared data. Right, can be modeled as follows. So we define a semaphore, right? Say the name is chopstick of 5. So all the elements of this particular semaphore type chopstick is initialized to 1. In a sense, it is available, right? So let's try to write that point as well, because that is important when we go to the programming part. Okay, uh, all the elements of chopstick they have to be initialized to 1. Okay, now let's go to the structure of a specific philosopher program. Okay, because we have multiple philosophers available, right? So let's write that the general structure of ith philosopher. Okay, and whenever we want to write a general structure of a philosopher, we'll follow this. That is, let's start with the do while, right? Initially I'm supposed to start with the weight. Okay, this is the weight of the chopstick. Okay, then we'll do another weight operation of this is the chopstick of, you see here, this is I plus 1, but I do percentage 5. It's a mod operator. I do a mod operation because whenever the weight operations happen to goes till 5, the next number is expected to be 0, right? So that's why this is the weight. Now we go for whenever the chopstick has been picked, because you see you need to pick up two chopsticks, right? So this is I and I plus 1, both have to be picked up, and when you pick both up you can eat. So you will write the program that is corresponding to eating part. Okay, once it is done, you can go with the signal part. This is signal of chopstick I. Then I perform signal of chopstick. This is I plus 1 mod 5. Then you go to, so once you finish eating, you get energy and you can go to the next job of a philosopher, which is to think. Okay, that's the code corresponding to think, and this has to be done always. So we'll write a while true. So the idea is very straightforward here. Okay, now if we think about this is a solution, right? Then this particular solution guarantees that no two neighbors are eating simultaneously. Okay, uh, whenever you try to generate a situation such as right, two people trying to eat together using this technique, if you try to do that, it ends in a deadlock. All right, so we'll write about that point here. So what are the solution advantages and what are the conditions on which it is like, uh, say I'll write this solution the solution guarantees that no two neighbors are eating simultaneously. It's obvious. Okay, so let us assume that say suppose all the five philosophers become hungry simultaneously, right? Each philosopher will grab one of the chopstick, maybe the left side one or right side one. All the elements of chopstick will now become equal to 0, right? Then when each of the philosopher is going to try to grab the right chopstick, it means it's not available. So when you see it is not available means what, right? It's actually a deadlock. Nobody is going to put it back because everybody is waiting for the next sorry, the next chopstick. So that's the problem, right? So everybody is trying to eat should be avoided somehow. So in this program we have not considered that part, right? How to uh, overcome the deadlock that is created. So we'll write one more point here explaining how the deadlock comes into picture, right? I'll just say it must be in the sense the neighbors should not eat together. That's the point. So it must be say rejected. It must be rejected because we now know that it creates a deadlock because it could create a deadlock. So how it creates a deadlock? Let's understand that with that example which I mentioned. So if all five philosophers become hungry simultaneously, And so each philosopher grabs the, say, one of them. It can be random, but let's fix it to one of them. So fixed one, that's a left side one, for simplicity. Okay. Everyone grabs the left chopstick. There are five chopsticks, and everyone will pick up the one chopstick which is present on their left side. Right? Implies, this means what? All the elements of chopstick, the variable chopstick which we have defined, will become equal to 0. Right? So this implies all elements of the semaphore called chopstick, okay, becomes equal to 0. It becomes 0. So it's not available now for anybody else, which means what? Which means until and unless every philosopher gets a chance to grab the right chopstick, it will be delayed forever. Right? So whenever the philosophers, all the five, uh, try to grab the right chopstick, this implies they are delayed forever. So it means it will never get a chance now because it's a deadlock. Right? So this implies deadlock. Now, so there are several other ways of getting a solution to the same problem, right? Which also ensures that there is no deadlock possible. We try to avoid a deadlock and we try to give a solution. Okay. So it comes in the next part, that is called as a monitor. So basically, if you use a simple solution of using semaphores, we will end up in deadlock, right? So semaphores are not complete solution for deadlocks. Okay, semaphores, even if we use semaphores, we have some, we always have some problems associated with the semaphores. Now, okay, let's look at the solution once, but we'll deal with the coding part later. So what is a possible solution? Yes. Okay, if we want to get a solution here, though there are five philosophers, you are going to allow maximum four philosophers to be sitting simultaneously at a table. So this is the possible solution which we discuss now. So we are going to allow maximum, so at most uh, four philosophers, to be sitting simultaneously on a table. Right. What happens when we do so? In the next step, we'll allow a philosopher to pick up the chopstick only if both are available. We will make sure that we are going to check that before any philosopher is going to pick up a chopstick, you are going to put up condition over there saying that we are going to allow only if, right, there are something like the condition is met. What is the condition? Allow a philosopher to pick up only if both chopsticks are available. So how this is going to help us, we'll see now. Okay, so the next point, allow a philosopher to pick up chopsticks only if, this is a must condition, only if both chopsticks are available. Okay, this means in order to do this, the picking up of a what do you call, chopstick, now we need to include that inside the critical section only, because when somebody is trying to pick up, others should not try to pick up, because I see that okay, both my chopsticks are free, but by the time I pick up, if somebody else will also think to access that, then you have a problem, right? That makes it actually a critical section problem itself, right? So we'll write that point here. This implies a philosopher must pick them up, pick them up under what condition? In a critical section inside the critical section. Only under this condition it is possible. Now let's, in the solution is extended further to use what is called as a asymmetric solution. In the sense, an odd philosopher picks up, right, the first left chopstick, then the right chopstick, whereas even philosopher picks the right chopstick first and then to the left. So you see that the accessing of the same philosopher, same chopstick by neighboring philosophers is going to get avoided under this condition. We'll put this also as a condition over here. Okay, so whenever the philosopher picks up, we'll separate them as a asymmetric part. Okay, so next one is to use an asymmetric solution. So what is that asymmetric solution? So this is any odd philosopher. We give numbers to the philosopher 1, 2, 3, 4, because we are going to, though there are 5, only 4 are allowed to sit on the table where they can eat. Okay, an odd philosopher picks up first the left, first picks up the left chopstick and then the right chopstick, and then the right chopstick. Okay, whereas and say even philosopher uh, picks the other way. Okay, which means picking up the right chopstick first, then the left chopstick. So, so we also have to take care that there should not be a condition that one of the philosopher will enter into the starvation. Okay, so because right now you are allowing only four philosophers to sit on the table where they can eat. So one of them is not getting a chance to to sit on the table. Right now, you should also should be taking care whenever you write a code that the one which was not allowed, right, is not going to get a chance at all. If that means it is a starvation, leads to death. Okay, so we have to uh, take care of that. Right, so this I'll write this solution must guard against the possibility that one of the philosophers will starve to death. So this means this particular solution, what we are finding out, has to be deadlock free, and also it should eliminate the possibility of starvation. So this means deadlock free and ELI elimination of starvation. So we understood that if we are using semaphores as they are, right, we may not get the ultimate solution over here. It looks like we have implemented the structure of a philosopher using semaphores, but when we analyze it further, we understood that okay, there is a possibility. Okay, because all the five picks means you have a problem. Okay, to overcome this, we have next type of structure that is coming up in an OS, that is called as monitors. Okay, now so we understood that semaphores provide a convenient and effective mechanism that's used for processing the synchronization process, right? And but if at all we use them incorrectly, this is going to result in the errors, basically timing errors. Normally this analysis is very difficult. We may not be able to detect the uh, timing errors related to the semaphores, and once you face that errors, right, execution of the sequence of the processes will not be so easy. Okay, so because of that, we go for a different idea here. Okay, so that different idea is what is going to be called as a monitor, right? And we get a new construct of data type used in the OS, which is called as, right, monitor. So previously we defined the whole new data type as a construct by name semaphore. Very similar to that, now we are going to create something called as a monitor type. We'll see now. Okay, so what is the meaning of this, and how we try to overcome? Okay, let's look at what are the errors, right, with the semaphore? If we try to understand the errors that might happen with the semaphore, we'll get a chance to uh, look at the solution as well. All right, so just because of that, let's try to look at a semaphore, and we discuss how semaphores give a solution when you enter into the critical section problem. All right, now let's say uh, all the processes share a semaphore. Whenever mutually you are trying to exclusive, you call it as a mutex. All right, we'll start from there, that point, just to understand the exact timing issue related with the semaphore. Okay, to understand the timing errors possible due to, so it doesn't mean that all the semaphores will generate a timing error. No, most of the semaphores solve the problem. But if we don't handle the semaphores carefully, then there is a possibility of timing error. Okay, so to understand this, let's consider a situation, right? Okay, let's reconsider. Let's reconsider a semaphore solution of a specific critical section problem. A critical section problem. All right, so we know that all processes are going to share a semaphore variable, say given a name mutex. Okay, so let all process all processes share what is called as a semaphore variable. Let's give a name mutex. All right, and we know that we have to initialize it, so let's try to initialize. Initialized to 1. This is the value, initial value of the semaphore. Now each process must execute a wait of this mutex before entering into a critical section, and whenever it is coming out, it has to execute the signal of mutex, right? So we know that already. So each executes the wait function of this variable, because this is the common thing. Okay, before before entering a critical section, before it enters, it executes that, and once it comes out, what it has to execute, it has to execute the signal of mutex. Okay, I'll just write afterwards. It means after it executes. Now let us say that there is a condition in which this sequence is not observed, which means two different processes may be in their critical section simultaneously, provided this particular sequence is not observed. We'll come to the exact meaning later, but let's just write now. So if this sequence, say is not observed. If at all this particular thing is not observed, right, then what might happen is two processes two processes may enter to their critical sections simultaneously. So this means uh, both of them are going to deal with, right, the same kind of variables whenever they enter into the critical section. Okay, that's one thing. There are other difficulties other than the handling of the common variables. There may be other difficulties. So this situation may be caused, right, by a programming error. Okay, simple programming error, because we know that the the usage of semaphores is actually for overcoming the problems of the commonly shared memory. But when we have uh, some issues with the programming itself, right, then even though we use a semaphore, we are not going to get an actual solution. All right, so let's look at what are the various problems that might occur, so that whenever we try to look at this problem, we can think of a solution which leads us to the monitor, the creation of the whole new concept called monitor. Okay, so now what might happen because of this whenever it enters into the critical section simultaneously, right? Now, it is just because of mishandling the weight and the signal functions. All right. So let's look at the first possible issue. Let's write, suppose a process interchanges the order in which the weight and the signal operations on the semaphore are executed. In the sense, mistakenly, you call signal first, then the weight. Okay. Suppose a process suppose a process interchanges the order of weight and signal, right? This means we first call signal of the variable mutex. All right, then let's enter into the critical section, and then you go for the weight of mutex. Now, in this situation, you see that several processes may be executing their critical section simultaneously, right? Because signal itself is indicating that others can enter their critical section. So whenever I call signal, assume the same scenario, programmer made a mistake in all the possible processes. He writes code for say 5 6 processes, and in each of the processes he writes signal of mutex first instead of weight, and at the end, after executing the critical section, the programmer writes the weight of mutex instead of signal. So their positions are interchanged, right? It indicates that as the program is getting executed in the form of a process, right, all the processes the programmer has written may be executing their critical section simultaneously, right? This actually violates the mutual exclusion requirement, right? So how you can discover this error? Only if several processes are right simultaneously active in their critical section, then only we will come to know that okay, there is a problem. Okay, right. So that's the first issue, right? Because of the programming error, though the semaphore is actually going to help us in overcoming this situations, but we mishandled them using uh, using them in a wrong order. Okay, so let's write this. So in this situation, I will repeat. So in this particular situation, we know that multiple processes are executing their critical section simultaneously. Okay, in this situation, I can write several processes may be executing their critical sections simultaneously. Right, so this actually means that you are violating the mutual exclusion requirement. All right, so how to discover this? Only we'll come by just looking at the program, we'll never come to know. We'll come to know only if, right, we find that several processes are simultaneously active, and it's not simply active, and every active process is running its critical section simultaneously, then only that's the problem, right? Even after using the semaphores, you have this situation, means you have a problem. Okay, let's go for another version of the problem. In this case, let's say that instead of calling a signal, right, the programmer calls the wait itself. So you call wait mutex, execute the critical section, and once again call the wait itself. All right, so this is another case. So if a process replaces signal of mutex with the weight itself, weight of mutex. So then this means let's write a general code over here. So you have, for example, you start with the weight. Normally I'm supposed to start with the weight, and I start with the weight. Okay, weight of mutex. All right, but as you enter the critical section, and you leave the critical section, I'm supposed to call which one? I'm supposed to call the signal. But instead of calling a signal, I'm going to call the weight itself. Okay, weight of the vertex. So weight means what? Initially, weight is going to give an indication to others that say other processes saying that okay, I'm executing the critical section. Nobody else should, right? So even after executing the critical section, you call the wait itself once again. So it means everybody will be waiting forever. So this means, right, this results in deadlock. This results in deadlock situation. It's obvious. Okay, then let's go to another case where the programmer omits one of them. Okay, So you write a process and you are going to omit either a wait mutex or the signal mutex, or maybe in both of them may be missing, right? So which means the mutual exclusion is violated, and once again the deadlock will come into picture. So let's write that quickly over here. In all the other cases, whichever that can happen, you may leave one of the wait, you may leave a signal, or you may leave both of them. Okay, if the programmer omits uh, a wait mutex, maybe, or the signal mutex, or both. In this case, what happens that, so weight is not mentioned means everybody will come, every other process will think that okay, nobody is executing their critical section, we can enter, so everybody will enter into the critical section. So means mutual exclusion is violated. So this means mutual exclusion is violated. So as soon as this happens, it means it is a deadlock. So it means though the semaphores are programmer friendly, uh, because of the programming errors, semaphores are used incorrectly and critical section problems will not get solved. Okay, in order to deal with such errors, right, there is another high level language construct created only to support the programs. Okay, so they are called as the monitors. So to overcome such, we can use a fundamental, it's a fundamental high level, high level synchronization, synchronization construct called, called as, right, monitor. So requirement of monitor means I just have to explain all these points. Okay, now let's look at how the monitor is going to look like. Now, whenever a monitor type is used in a program, right, uh, we actually define the operations that are provided mutual exclusion within the monitor. Okay, so in general, a monitor type uh, is basically, it presents set of programmer defined operations. They are going to be mutual exclusive. Like whenever we define a monitor, we need to make sure that okay, there are several procedures, right? User defined functions, like they are mutually exclusive. That needs to be present first. Okay, all right. So let's try to give the details of the monitor now. So the monitor's details are as follows. Uh, a monitor encapsulates, it encapsulates private data with public methods right? So we are going when we define this now, we are going to see that there will be private data and public methods to operate on the data which we define. So private data will be defined and public methods to operate on them. In the sense, whatever data you define, we are going to use uh, public methods. Okay. Now, now whenever we call a monitor, whenever we define a monitor, it has set of functions, that is a public methods, whatever we call. It's actually a user defined, in the sense the programmer defined operations. Okay, so let's write that a monitor presents a monitor presents a set of programmer defined operations, okay, that provide mutual exclusion, right? So in the sense, we are going to define some function, user defined functions, and those functions are going to take care of the mutual exclusion. These functions will be seen inside the monitor whenever we define that. This is the first condition. It also actually contains some declaration of the variables whose values normally define the state of a particular type, okay, which functions are operating on those variables, what is the status, okay, what is the state of, right, the procedures or the functions that operate on the variables, right? So we have some variables also coming into picture, right, because we say that okay, there is some private data. So what private data we are going to write? It actually a set of variables. Okay, I'll just write monitors also contain declaration of, say, variables whose values define the state of the state of any instance, or I can write any instance, an instance of that type. That type refers to the type of the variable which we define. In addition to this, I can write along with, in a sense, when we define when we give a value to this variable, uh, it's going to give some more details. So along with the bodies of procedures, along with the bodies of the procedures. So procedures are already defined, and procedures, or we can call it as a functions, procedures or functions that operate on those variables. So we are going to get the status of the function or an instance of that variable which is being used. Okay, now let's go to the syntax of a monitor. So how the monitor is going to look like. So general structure of a monitor. general structure of a monitor. So the keyword used is monitor itself. So previously we used to use the semaphore by the keyword semaphore itself. Okay, so I'll write the name of the monitor. So that is monitor underscore name. You can give some name. All right, then open this. So whatever variable you want to define, you can define here. That's called as the shared variable declaration. Okay, so that will be done over here. Then go to the private procedures. That is a procedure. Procedure, maybe a name is given p1 and you declare what variables you are going to pass. Okay, then we open this. I write the contents of this procedure and I'm going to close this. Okay, let's go ahead and then we write the procedure. Okay, procedure p2, we write something, write the procedure, close it. Okay, in the same fashion you are going to write many procedures, and let's go to the nth procedure just to finish it up. Procedure pn, open, pass the variables, open the bracket, write the function, close it. Once this is done, the next part of uh, the monitor will contain a specific code called initialization. This is called as initialization code. Again, you can pass some variables to that. You can open, write it, write the code, close it, and then close the main flower bracket, which was opened immediately after calling the monitor name.
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.